So, hi everybody. First of all, I would like to thank the organizers for the opportunity to present my work here. The work is called DUNE Potential as a New Physics Probe. I myself is Adriano Cherchiglia. I'm from Unicamp, and this work was done in collaboration with José Santiago from Universidade of Granada, and this work was published at JHAP, and this is the reference if you want to check it out and check more details. So let's get started. As we all know, because here in the conference are mainly neutrino physicists, so there is a very exciting neutrino experiment program in the upcoming years. Here I'm just bringing to you three experiments. So we have Juno, we have the Hyperkamiokande and DUNE, and I'm mainly focusing on DUNE in my talk, but in principle the framework, everything I'm going to develop here is applied for any kind of long baseline neutrino experiment. So you can apply this for other long baseline neutrino experiments, but you can also actually modify it a little bit and apply it to other kinds of experiments as well. So what is the main goal of DUNE? As you also know, the main goal of DUNE is actually to measure the three remaining parameters in the three-neutrino standard paradigm with precision. So one thing we would like to know is which is the ordering, if it's normal ordering or inverted ordering. Particularly, we would like to know if there is CP violation in the leptonic sector, so it's actually one of the main goals of DUNE. And also we would like to know the octant of the theta 2,3. So everything is very nice. So this is the goal for DUNE, actually, to measure these three parameters with precision. But this can only be applied, or actually can only be achieved, if BSM effects are actually small. So this actually was discussed in the literature in a lot of papers by doing different things. But in a general way, what we can do, what are the BSM effects that can show up in a long baseline experiment? So basically, we can actually introduce BSM effects at production or detection. So you can modify these guys here by modify something in the production of the neutrino by pion decay, or modify something in the detection for the argon, right? When the neutrino is interacting with argon. And what will happen is that if you modify these guys here, if you modify any of them, you just modify the neutrino event rate that you are going to see in the far detector. For here, for my talk, I'm going to consider BSM effects at production or detection with the epsilon bar. So the bar will be for NSIs at production detection, which actually are the charged NSIs, right? So they are actually related to the charge current. But you can also have NSIs at the propagation, because DUNE, for instance, DUNE, you have a very long baseline, so neutrinos can interact with matter, and in principle can also interact with other BSMF particles. So in this way, you also have the NSIs, which are known as the neutron NSIs, the neutral currents NSIs, and here, as a standard, I'll just use the epsilon, okay, for the neutral NSIs, the neutral currents NSIs, and as well, if they are there, they will just modify the neutrino event rates that you see at the far detector. So that's very nice. That's a very phenomenological way to see how BSM effects can show up in a long baseline experiment like DUNE. But you can also think in a more broader way, because as we know today, we have the standard model, which is very nice, but it has a couple of problems. So one of the problems is that it does not provide a mechanism for neutrino masses. It's not there. You don't have also a dark matter candidate, so it's also missing. You don't have a compelling explanation for matter and antimatter asymmetry. It's not there as well. And you can also think in other problems. So you know that the standard model has all these kind of problems, but you don't know where to go. So actually you have an ocean of theories, actually with very different islands. Each island is like a theory or a group of theories, and a theory will be just, let's say, a point in this kind of islands. So you have all these sea, and you don't know where to go, where you have to ship from the standard model and disembark in which island here. So what we do as particle physicists, theoretical particle physicists, you just choose a model in principle. So you have to choose a model here in one of the islands and use some kind of effective field theory. This is because you have in our minds that these particles here will be heavy, so actually they are above the electric scale. So in some sense we integrate them out, and you just see how this theory affects the neutrino event rates. So you can do that, and in principle you have to do that for all the theories that you are wanted or you are interested at. So in principle you can do that, but in principle, can you think in a more general way of doing that? Maybe you don't actually can go to all the islands and all the points in the islands, but maybe you can go and build something that's general enough that actually helps you. So it actually gives you a more broader way of what's happening. So that's exactly what we want to do. So what we want to do is actually to have some kind of dictionary, which you just have so many theories here, so many points, and you want to connect all these points to the neutrino event rates at once. And this can be done because in the group of Granada, they actually built a kind of dictionary. And this dictionary is a dictionary for UV models. So what you have is just the assumption that the standard model gauge group is this group. So you just write all the particles, all the fields that you can with this group up to spin 1. And once you have that, you can actually integrate to this math, and afterwards integrate to the left. And just to remember, in this math you have all the particles, all the fields in the standard model, and in the left you actually integrate out some of them. So integrate the W, the Z, integrates the Higgs, and also integrates the top. So you have the left with the low energy effective field theory. Okay? And in principle, is this guy, is this effective field theory that you have to use when you are talking about the neutrino experiments, and in principle when you are talking about the NSIs. So this is the goal, actually, to build all this chain, and that's exactly what we have done. So in our paper, what we did is actually to build this chain. So you have all these models, and now you know exactly how they affect NSIs, how they generate the NSIs, how are the parameters that enters in the NSIs from the UV model. So everything is there, and everything is very concisely done in this GitLab. So you can just go to the GitLab and all the chain there is there with some examples, and you can use it and to check which model actually will affect NSI that you are interested in. So everything is very good, and this is actually done very, very generally. But of course, neutrino experiments are not the only thing that are going to constrain UV models. You also have other things. And for other kinds of experiments, in particular with charged leptons, so you have the charged lepton flavor violation process, which have been searched for a long time, and you haven't seen any of them. Actually, these will provide very strong bonds in the Wilson coefficients that are in this math and afterwards enter in the NSIs. So the main point that we are going to get from here is that by considering these processes, all the non-diagonal NSIs are basically zero. So everything is basically zero. You only have the diagonal ones. And once you have that, once you have only the diagonal ones, in the production, actually the NSIs will cancel in the event rate that you build for the neutrinos. So they just cancel, you don't have anything else. So the production, for the production, the NSIs doesn't play any role. They are there. So if you have a UV model that also generates NSIs at propagation, but also at production, they will be there. But the point is that DUNE will not go into see them. They just cancel in the event rate. And for the other NSIs, for the NSIs at propagation, you have these guys at the diagonal, so you can actually probe them, and this is what we are going to talk afterwards, okay? So let's go. So once you know that only diagonal NSIs can be constrained, these guys here, as I told you before, so what we can do actually, what is the next step? Once you know that, you can actually go and see by doing a global fit, which are the bounds that you have at the Wilson coefficients that enter in these guys, right? So we did that because you know now, right? You have the chain, so actually know the Wilson coefficients that will go into affect these guys, and you can use a global fit, a result of the global fit, to actually see how large then they can be. And also one very important thing is that for DUNE, the NSIs can be probed if they are up to 10 minus 2 more or less, okay? And this translates in this plot if you have the Wilson coefficients of order 1 TV minus 2, okay? So have something f order 1 or up, in principle DUNE can constrain, and if you go to the other direction, to the left here in the plot, DUNE in principle cannot constrain them. So as you can immediately see, there are three guys that are quite promising. These guys here, because they are multiplied by 10 to minus 2, which are connecting tau. So you have taus connecting with the quarks. So these three guys can be very important for DUNE. And also there is this guy here, which is connecting the muon with the down quark, okay? And which kind of models you can have this kind of guys? In principle, this kind of guys show up in models with leptoquarks, and also with a model with a Z prime, or in other ways, a vector boson that is actually neutral. And these are actually the only models that can be probed by DUNE. So that's actually a very strong statement that you have showed in our paper. So here, just to show you an example, you actually have chosen two models here. So actually go to two islands there and choose two models. These models contain leptoquarks. So you have just one model, one of those models just contain scalar leptoquarks. The other one contain vector leptoquarks. And then we actually use our chain and see how the NSIs, the event rate will change, okay? So here are the results. So here in this area, in this round area in the ellipsis, what we have is these confidence levels for this NSI. So you have here epsilon EE minus epsilon mu in the y axis, and the x-axis you have the epsilon tau tau minus epsilon mu mu. Okay. So in blue you have the 9% confidence level that DUNE can actually probe. So actually it's the sensitivity of DUNE for these particular guys. And this small band here is the band that's predicted for the model. So you have this model with scalar leptoquarks, and that's the band that can be predicted by the model. And it's very interesting, if you see here, there is this gray area here, and this gray area is actually the constraint that you have for this particular model today. So today you have this constraint, but when you build DUNE, in principle, DUNE can actually help constrain this model even more, because you can go to this region here, okay? So you can constrain this model by DUNE, considering the present current bounds, okay? This is for the scalar leptoquarks, and this would be for the vector leptoquarks. So for the vector leptoquarks, actually there is much room to actually constrain the model much by DUNE. Okay, so this is just an example. I have just chosen this with the leptoquarks, but you can do whatever you want. You actually have any numbers of fields that you want. Everything you can just do that, put there, and then you get the NSIs, and then you can check for DUNE or for other experiments that you are interested in. Good. But now you can also think a little bit beyond this method, because everything I'm talking about here needs the following. Needs that you start with a dictionary and then go to this method. In other words, all the new particles are heavy, right? So they are above, the mass of these particles are above the electric scale. But in principle, this cannot be, maybe not true. So you actually can have some light particle, let's call it an X, and this light particle has a small mass comparing to the electric scale, but was not discovered because its couplings are very slow, very small, or something like that. And in principle, this particle could be as light as light that it can actually go to the left as well. So you have in the left also this particle X here. But of course, since you don't know this particle here, you cannot do a complete picture, okay? So you cannot do that for all the models because you don't know the X. So for each model that you want, for each X that you want to be light, you have in principle to do all this chain. Okay, this can be done. But since we would like to have something more complete, more general, we didn't do that. We didn't choose an X and study this scenario. But what we did was just a global fit. So actually we did a global fit using globes, And for this global fit, we consider it two scenarios. One of the scenarios, the NSIs are real, so we have the NSIs at propagation and production at the same time, and all the standard parameters were fixed. So we fixed everything using the results of new fit. And this would be an optimist scenario, like if these guys could be fixed or could be very well measured somewhere, and then we just would like to know how extringent can be the bounds on the NSIs from DUNE. Also, to be more realistic, what we did was to vary these guys here. So all these parameters, the 4 parameters, we varied at 1 sigma level, and the NSIs were also allowed to vary. Actually, we are going to constrain the NSIs. They are also real as well. And we studied also this scenario here. So the results I'm going to show here is just for this scenario, which is more realistic. So these are the results. These are for the propagation. And for the propagation, one particular interesting channel is this one. So you have the epsilon E mu and epsilon E tau. That DUNE can actually provide a good constraint, because here in this square, here in this square is the allowed region by today. Okay, so these are the bounds, the present bounds from these guys. So we have these present bounds here for the epsilon E tau, the present bounds for E mu here, and this is the region that's allowed. And actually DUNE can in principle constrain these two guys quite a lot. For the other guys, DUNE are not going to provide a very good improvement. And that was for propagation. And now for production, in principle DUNE cannot provide a lot of new things, actually new constraints, because from pion decay there is actually a very already stringent bounds on these NSIs, and DUNE can in principle not provide very much improvement here. So just to conclude, there is actually exciting new results for neutrino experiments in the coming years, and for DUNE in particular, we showed how we can perform a mapping all the UV models that can be constrained by this experiment, and we end up with models with leptoquarks and with a Z prime. And also, going or thinking about beyond this method, we performed a global fit for NSIs at propagation and production, which here the idea is to have a guide for model builders. So if you are thinking about a model with a light particle and you want to see how large DUNE can constrain this particular NSI that my model is predicting, you can actually go to the global fit and actually have an idea of that. And as before, everything, the chain is here in the GitLab. So thanks a lot.